I am Eleni Sapridou, and I will present joint work with Ioannis Mitilinis and Anastasia Elamaki on partitioning for data streams. Concretely, in this talk, I will tell you how we can leverage online learning to design a partitioning technique that scales not only the processing nodes, but also partitioning itself. To be able to process large volumes of data very quickly, streaming systems rely on parallelization. So they scale out execution, creating multiple instances of the same operator. On the slide, you see a simple group by aggregation query, where data arrives at the source operator, then gets propagated to the partitioner, and then the partitioner is responsible for deciding for every tuple to which instance of the group by operator to send it to. Now, since in this case we're doing a group by, the natural way to partition the data would be to do hash partitioning and basically send all of the tuples that have the same partitioning key to the same worker. However, if we do that and the data distribution is skewed, we will end up with some workers being overloaded because they're processing the most frequent keys, while others are being idle waiting for data. Now, someone could think that we can find an ideal hash function that perfectly balances the load, but this would only work momentarily since we're talking about data streams, and so the distribution changes at runtime and can change quickly. So the first goal that we set for stream partitioning is that it should be able to adapt to the data distribution. Now, even if we manage to do that and we have a partitioner that perfectly balances the load, irrespective of the distribution, we're still not done. Streaming queries often require processing data from multiple different data sources and can have a high degree of parallelism. In this case, if we have a single partitioner, this means that the partitioner would need to communicate with all of the data sources and all of the downstream operators. So partitioning itself can actually become a bottleneck. So the second goal that we set for stream partitioning is that it should be able to scale to multiple partitioning instances that operate concurrently in the system and achieve load balance for the whole system. In this work, we focus on group by aggregation. And as I said, the natural way to partition the data in this case is to do hash partitioning, but hash partitioning is not effective if we have a skewed data distribution or if the number of keys is smaller than the degree of parallelism in the system. For these reasons, key splitting was proposed, which is considered the state of the art. And what key splitting does is that it splits the group by aggregation step into two stages, the stage of the combiners and the reducers. So at the first stage, we allow the same key to be processed by multiple combiners, because then the reducers aggregate all the partial results for the same key and produce the final result. Basically, you can think of it as MapReduce. The advantage of key splitting is that it gives us some flexibility at the step of the combiners, and so we can split very frequent keys to multiple combiners, and hence it's easier to balance the load at this stage. However, the disadvantage is that the bottleneck can actually shift to the reduce phase. Actually, if we want to guarantee load balance for the step of the combiners, we would do round robin, but then we might increase drastically the number of intermediate results that we send to the reduce phase, and so the reduce phase can become a bottleneck. So let's see how these two approaches can adapt to the data distribution. For hash partitioning, adapting to the data distribution would mean that we would change the hash function as the data distribution is changing, and this would require state migration. State migration is, however, expensive, as it typically requires pausing the whole system for some time. Now, for key splitting, adaptive approaches have been proposed as well. However, they incur a high per tuple overhead, and also they assume a centralized partitioner that keeps some statistics for the whole system, and so they're not able to scale to multiple partitioning instances. In this work, we propose Dalton that achieves both adapts to the data distribution and scales to multiple partitioning instances. So let's see how we achieve that. Dalton relies on key splitting, so its goal is to balance the load at the stage of the combiners and minimize the cost of the reduce phase. And how it does that is that for every tuple that enters the system, Dalton would forward it to a contextual bandits agent. And then the agent decides between performing exploitation or exploration. When the agent performs exploitation, it basically makes a decision based on past experiences. Concretely, the agent will consult a Q table that stores learned costs. So the Q table essentially keeps for every partitioning assignment, every combination of a key and a combiner, what is the cost that the partitioner has observed so far for this assignment. And here, instead of simply averaging all the costs for this assignment, we are actually using a discounted average so that we ensure that the decisions of the partitioner depend more on more recent rewards that are about the current data distribution. Now, from time to time, instead of performing exploitation, the agent will choose to perform exploration in order to check whether an assignment that has not been made for some time is actually beneficial for the current data distribution. So either through exploitation or through exploration, the agent will choose a worker, a combiner, and the tuple will be forwarded to this combiner. Now, for keys that are not very frequent, we chose to assign them using a simple hash function, since if the key is not that frequent, we don't need actually to split it across many combiners, so using a hash function is actually cheaper. If in our system we have multiple data sources and a high degree of parallelism, we would need to use multiple partitioners, so that partitioning is not the bottleneck. But if we trivially just add multiple Dalton partitioners in our system, what would happen is that every partitioner would take actions, basically make partitioning assignments and calculate their costs. And then from these costs, it would derive a local policy that balances the load from the corresponding data source. However, the combination of these local policies might not be optimal for the system as a whole. Our approach has a nice property that we can use here, which is that the Q tables store information about the keys that are hot for every local distribution, and also a policy that is optimal for the local distributions. So what we do here is that we add an extra operator that we call the Q table reducer that communicates with the partitioners and receives from them the Q table at every synchronization point. Then the Q table reducer would find the keys that are hot for the global distribution. It would find a global policy for every key, and it would broadcast this policy back to the partitioners. Then the partitioners make decisions based on this policy and build on top of it as they learn more costs until the next synchronization point. Now, a good question here is, how do we ensure that the communication between the partitioners and the Q table reducer itself does not become a bottleneck? So for this purpose, we propose a protocol with which the partitioners and the Q table reducer can ensure that can reconfigure the synchronization frequency at runtime, ensuring that it's not a bottleneck. So there are two cases. The first case is that if a partitioner sends a message more frequently than it receives a message from the Q table reducer, then it will realize that there is a queue at the Q table reducer, and so it will ask for the synchronization frequency to be decreased. The other case is if the Q table reducer spends most of its time being idle instead of processing messages, then it will increase the synchronization frequency. So the goal here is to find a sweet spot between synchronizing the partitioners as frequently as possible, while at the same time not having all of this communication be a bottleneck for performance. I will move now to experiments. So we use a cluster with 5 machines, and we deploy Dalton, our algorithm, in both Flink and Storm to show how it performs both for the tuple at a time and the microbatch model. However, in this talk, I only include experiments with Flink, and I will use the task of word count and a sliding streaming windows with a size of 60 seconds and a slide of 1 or 20 seconds. Let's start by a scalability comparison between Dalton and the other partitioning algorithms. So on the x-axis of this slide, you see the number of threads, and then on the y-axis, the throughput in thousands of records per second. With shades of blue, you can see hash-based approaches, and what we can observe is that they do not scale because they are bottlenecked by the most frequent keys, since the distribution in this case is skewed. Then we have key splitting approaches with shades of gray colors that scale better because of their ability to split the load for the frequent keys to multiple combiners. And finally, we have adaptive key splitting approaches with shades of orange color. From what we can see is that from all the algorithms, Dalton performs the best, giving up to 4.6x speedup. And the reason why Dalton performs better than the other adaptive approach is that DAGRIDI, which is the other adaptive approach, would need to calculate all the cost for all the possible assignments before it decides what assignment it will perform for a tuple. Next, I want to show an experiment where the data distribution is changing at runtime. So here we have on the x-axis the event time in seconds, and on the y-axis the throughput in thousands of records per second. And the distribution changes from uniform to skewed, and then again uniform and skewed. So what we can see is that the hash-based approach performs the best when the data distribution is uniform, but then is actually the worst approach when the distribution is skewed. While key splitting approaches, when the data is skewed, actually do better. Then adaptive approaches manage to adapt, and we can see that Dalton, when the data distribution is skewed, outperforms all existing approaches, and so it is the only algorithm that has the best performance across all distributions. Finally, we compare the performance of all algorithms when we use two sources and two partitioners. In the first set of bar plots, we are using a source that is producing data from a uniform distribution and another source that is producing data from a Zipf-ian distribution. And in the second set of bar plots, both sources produce data in a Zipf-ian distribution, but we're using a different set of hotkeys for every distribution. So what we can observe here is that Dalton manages to outperform existing approaches and give up to 4.4x speedup due to its ability to coordinate all the partitioners and derive a global policy that balances the load for the whole system. So we observe that there is not a single partitioning technique that both adapts to the data distribution and is able to scale to multiple partitioning instances. And we propose in this work Dalton that is able to adapt to the data distribution because it learns from its previous assignments and then it makes quick decisions based on past experiences, and also is able to scale to multiple partitioning instances because of its ability to coordinate the partitioners and derive a global policy based on the local experiences that the partitioners gather. Dalton outperforms existing techniques by up to 6.7x.